So this is the part where we had stopped on Wednesday. We had started talking about um, how to design a field trial for a given vaccine, and we had looked at two different designs for this experiment. The first one was observed control, which was the case in which we were comparing second graders to first and third graders. And we said, this is maybe an okay design, but it has some flaws. And the flaws in particular came from the fact that we were comparing all first and third graders to second graders that had given consent, which might differentiate it might make the populations that I am comparing quite different, right? So that's something we had discussed. And then we had talked about placebo control, which we said was actually pretty nice because it allowed us to have a double blind in which both the people that were participating in the trial, so that means the children, and the doctors who were providing the vaccines, did not know who was being treated and who was not being treated. And so that might not bias the results, right? So these are the two results that the two designs that we discussed. And what we're going to do next is look at the results that were actually obtained. Now, of course, I don't want you to copy all of the information that I'm going to show in the next table. I just want you to look at it, and then we can discuss, what you think from that information, what you see, what's interesting about it, and so on. Okay, so don't freak out. It's a huge table. You don't have to copy the information here. I just want to discuss. You have the video always to go back to and see that information. Okay, so here's the table. Okay, now let me just guide you through what you're looking at here. Again, just very, very big table. But what we're really interested in is the total cases of polio, and we want to compare what happened between the two populations that were being compared, right? So in the placebo control trial, that meant comparing the vaccinated children to the placebo children, so the ones that had gotten a vaccine versus a placebo. And the second option was the vaccinated children versus the control children. And in this case, the controls were not placebos, but rather the first and third graders population, right? So you can see that over here. Now, one thing that I want to remark upon is the fact that you're looking at a rate here. Okay, so you're not looking at the total number, you're looking at a rate, which means that you have already rescaled with respect to the population. So maybe you had a lot more, so for example, here, you had a lot more children in first and third grade than children in second grade that gave consent, which means that we don't want to compare the numbers because those are, of course, going to be very different. What we really want to compare is the rates, okay? And these rates are expressed in terms of cases per 100,000 people. Okay, so cases per 100,000. Can I see a show of hands for everybody that's following that? Okay, so we have that these are the cases per 100,000 people, and what we wanted to determine is if the vaccine was effective or not, right? If we want to determine if the vaccine is effective or not, that means we want to determine if vaccinated children were less likely than placebo children to contract the virus, right? Or if vaccinated children were less likely than control children to contract the virus, right? Now, in both cases, over here, we can see that there seems to be a difference between the rate of cases between the vaccinated and between the control, whether that is the placebo control or just the observed control. So we have that it looks like maybe there was a decrease in the probability of contracting the disease for children who had been vaccinated. Can I see a show of hands for everybody that agrees with this? All right. So I see 21 hands up. Do I have any questions? Anything that's not quite clear yet? Okay. So we have this difference between vaccinated and placebo, and this difference between vaccinated and controls. But the problem is that we don't necessarily know if this is caused by chance or not, right? So we could very well say, okay, well, now I have these numbers, and those numbers are nice and everything because they give me an idea of what I observed in the data. But what if this was just luck? What if these 28 children were going to get polio whether they were vaccinated or not? Or what about these children that got the placebo? We're going to get the disease whether they got the placebo or not, right? Isn't it possible that it just so happened that when I separated my my placebo children from my vaccinated children, I split up the group of children that were going to get the disease anyway into these two groups in such a way that I ended up with 28 in the first group and 71 in the second group, right? Isn't it possible that maybe out of luck, the first group, the vaccinated group, ended up with fewer students that were going to contract the virus anyway, and the placebo group ended up with more children that were going to contract the virus anyway? Can I see a show of hands for everybody that understands this question? Yes. Okay, I'll repeat it again. So you can see here that we had 400,000 more or less children that got that participated in the study, right? And then we assigned them randomly into vaccinated or placebo. So they either got the vaccine or they got something that was not the vaccine, right? From these children, we placed them randomly, and we got that in total 199 of them. So 142 plus 57, 199 got the virus, right? So 199 got the virus. Now I'm saying that it looks like the number of children that got the virus and were vaccinated was a lot lower than the number of children that got the virus and had received the placebo. So what I'm asking here is, okay, well, maybe these 199 children were going to get the virus anyway, and maybe the fact that I just have fewer of them in the vaccinated group is just due to random luck. Maybe it just happened that these 199 children were going to get the virus regardless, right? Whether they got the vaccine or didn't get the vaccine. And therefore, that the vaccine didn't have anything to do with the fact that this number was small. Right? Isn't it possible that just by luck, the children that ended up getting the disease were divided into 57 into the first group and 142 in the second group? Can I see a show of hands for everybody that understands this? I can repeat again. Okay, I'm seeing 22 hands, and this is kind of like the essence of the next 10 or 15 minutes of the lecture, so I need to make sure that everybody understands. I have still about 4 hands that are not coming up. I will call out names if I need to. Just need everybody to understand. All right, very good. So what we're trying to determine is, okay, isn't it possible? Now I'll do the graph because I always do better with little figures. Isn't it possible that, I had a population of 400,000 children? And what I'm saying is maybe out of these 400,000 children, I had that 199 of them were going to get the disease anyway, right? Regardless of the vaccine or not. And maybe what happened is not that the vaccine made it less likely to get polio, but just that in randomly assigning them to two groups, I ended up by luck assigning fewer of these children to the vaccinated group than to the placebo group, right? So is it possible that when I split them through random assignment, is it possible? So here, I know that I randomly assigned random assignment. I know that I assigned more or less 200,000 of them to the vaccine group and 200,000 of them to the placebo group, right? So the question is it possible that just through random assignment, I might have divided this group of 199 into 57 for the first group and 142 for the second? All right, this is the question that I'm trying to answer. Now, again, just for next check, can I see everybody that understands this? Okay, so just for precision, what I'm saying is that the green blob over here represents the children that were going to get polio anyway, and ended up just dividing them in two in such a way that 57 ended up in the first group and 142 ended up in the second group, right? Now, the advantage for me is that I can actually do the calculation for the probability of when this is going to happen. When is this distribution, when is this split of 57 versus 142 going to happen? And in doing that computation, I can try to determine whether this is actually likely. So is it possible that I had students that were going to get polio anyway, and they were divided in this way? If it is possible, then maybe I shouldn't attribute the low number over here to the vaccine, but just to random chance. But if this is very unlikely to see just by random assignment, then that might mean that the vaccine has something to do with the low number of vaccinated children that got polio. Can I see a show of hands for everybody that understands this? And I can repeat again, so you can always ask me to repeat. Okay, so what I'm saying is, because I have random assignment over here, because I randomly split this into 1 and 2, I can use probability theory, right? I can use probability theory to see how likely it is that 57 of these 199 ended up in the vaccinated group, and 142 of the 199 ended up in the placebo group, right? If it is quite likely, if it is pretty common that this split happens, then that means that the fact that there is a low number of polio children in the vaccinated group could just be due to chance, right? So if this split is pretty likely, that means that this low number might just be explained by random chance. And so that means that my vaccine is not necessarily as effective as it looks. So far, so good. Can I see a show of hands here? All right, so I'm going to try to determine if it's likely, and if it's likely, then that means that this is pretty okay. And so the fact that there's a low number here is not due to the vaccine, but just due to random chance. But if this split over here is very uncommon, if it's very unlikely that I get such a low number in the vaccinated group just by random assignment, then that means that the reason that this number was low was not the random assignment, but rather the fact that the vaccine works. Now, can I see a show of hands for everybody that understands this? All right. Okay, so that's what we're going to try to see. So I'm just going to summarize this. So if this split is very likely, then the low number, so the 57, can be explained by random chance, And therefore, maybe the vaccine is not the reason. That the number was so low, right? But if the split is very unlikely, then the 57 is not likely to be explained by random chance. So the 57 is not explained by random chance. And so it must be the vaccine that caused this number to be so low. My writing here is horrible, but you get it. Sarah, was that enough scrolling up?
Yeah, I just had missed one thing, so thank
All right,
you.
okay. Okay. Can I, everybody lower your hands for 1 second? I'm going to ask you to lower them, to raise them again pretty soon, but just want to make sure that everybody's actively pressing the raise hand button. Okay, now I want to see everybody that understands the logical argument behind this. I want you to raise your hand. So the logic behind how we're reasoning this out. I want you to raise your hand, please. Seeing 22 hands. Still looking for, I think, like 6 maybe. Okay, good. I see. Understanding it's normal. It's a complicated argument, but I want to introduce it early so that because we're going to use this argument over and over again during the semester. Now, lucky for us, we know how to do probability theory, or we will at some point. But more importantly, I can run simulations on my computer. So I can try to say, okay, well, I can simulate a population of 400,000 things where 199 have a single property. And then I can simulate this assignment a bunch of times, right? So I can randomly assign, so like I do this, I split it once, and then I split it again. And every time that I split them, I count um, how many polio cases I got in the vaccinated group. Okay, so what I'm doing is I'm simulating. So what we can do is simulate. I think I did it 10,000 times, so 10,000 random assignments. And every time, for everyone, every, whoops, one of them, we count the number of polio cases in the vaccinated group. I don't know why I wrote a question there. In the vaccinated group. Then, if 57 happens often, then we're in case number 1 over here. Right? But if 57 doesn't happen often, or happens very rarely, then we're in case number 2. At this point, could I please see a show of hands for everybody that gets that? Okay, so what I'm doing is because I can't, like in real life, I can't run this experiment 10,000 times, 100,000 times, or whatever. I can do it with a computer, and then the computer is going to tell me how likely it is that I observe the values that I did observe. So I did that. I generated 10,000 10,000 random assignments. And this is what I got. Okay. So what's happening is that every single time I'm splitting the 199 cases into two groups, either the vaccinated or the polio. Eventually, we're going to do that with our studio. Yes, that's why we want to do it. Now, reasonably, you see that most of the times, because you're splitting 199, no, you don't need to copy this. Just look at it, understand what I'm saying, and that's fine. Because you have 199 cases of polio, right? You have 199 cases of polio, and you're randomly, well, supposed cases that we're going to get polio anyway. What we're trying to do is randomly assign them to two groups, the placebo and the vaccinated. And so it makes sense that most of the time, so most of the times here, we're going to have about, half of those cases in the group with the vaccine. And so about half the times we're going to have half those cases, but most of the time we're going to have half of those cases in the vaccinated group. Can I see a show of hands for everybody that understands that? Right? It makes sense that most of the time I have about half of the 199 within the vaccinated group. Okay, so again, I'm trying to split these 199. So I'm splitting the 400,000 into two groups. And so this 199, most of the time, are going to end up being evenly distributed between this group and this group, right? So that means that most of the time, by dividing this 400,000 into two samples here, into two groups, I'm going to end up more or less evenly splitting the 199 as well. Can I see now a show of hands for everybody that understands that? Okay, seeing a lot more hands. Okay, that's good. So because most of the times I'm going to evenly distribute them, then that means that most of the time I'm going to get about, 99, 98, and so on cases in the vaccinated group, right? Sometimes, just by random chance, I'm going to have some more than those 99.5 or some less than those 99.5. Right? And this is just because of random chance. Maybe sometimes I end up picking a couple more, I end up picking a couple less, and that's that. But the most important thing that I want you to remark upon here is that the lowest value that we got is higher than 70. Right? The highest value that I got was even higher than 70, and what we were looking for is how likely it was for us to get, okay, well, I can't seem to align them. Go. What we were looking for is how likely it was to get 57. So if 60 is around here, we were trying to get how many times we could see 57 cases just by random chance. Right? What we were trying to determine is how likely was for me to get in the vaccinated group 57 cases just due to random chance. Can I see a show of hands for everybody that understands this, please? All right, I'll take your question in just a second. First, let me ask you a question. So how likely is it that we observed 57 in the first group? Essentially zero, right? Probably if I did maybe like 100,000 or a million simulations, I would get one lonely simulation that ended up here, but it is very unlikely. Most likely, I'm going to end up with about 99 cases or 100 cases, and it's very unlikely that I end up with 57 cases, so with only 57 of the 199 cases in the group that was vaccinated. All right, so it is very unlikely to have only 57 cases, polio cases, in the vaccinated group? Just by random chance. So according to you, what's the conclusion here? That's right. The vaccine seems to have an effect because the low number in the first group cannot be explained just by random chance. So there must be something else at work, right? If random chance is not the reason why I can explain this, then there must be something else that's going on. And that something else that's going on is the one thing that we made sure was different between the groups, the one thing that we were controlling, and that means that that's the vaccine. So the vaccine seems to be the reason. Okay, so the vaccine seems to be the reason for the low number, and therefore we can say, okay, well, it seems like this is the reason, and the vaccine was effective. Okay, so the vaccine decreases the probability. Okay, so I have 3 questions in line. The first thing is I want to know what Lori means by genetics.
Because like, what if like the kids? Okay, no, never mind. I think it brings in the kids that like we're going to get polio anyway. So never mind.
Right. So if the difference is like, oh, maybe like these kids were genetically different, that's perfectly fine. But the thing is that because we randomly assign them to one group or another, we have kind of evened the ground and made sure that it's just as likely for a child with genetic conditions or economic conditions or like just environmental conditions that are, like kind of like in favor or against of one of the outcomes, they're as likely to go into one of the groups as the other. Right? And so that's the advantage of doing the randomization and the placebo, right? Okay, Rita, do you have a specific question? So like a point at which you got lost?
I'm just confused because now I feel like numbers are getting higher. So if they're getting higher, doesn't that mean that the vaccine actually did not work and that was just by luck that the number was low?
So do you mean like these numbers were higher?
Yeah.
Okay, so what this is representing is what would happen if it was due just to random chance, right? So if I had 199 children that were split into 2 groups just by chance, right? So if these polio cases were going to happen anyways, and I ended up splitting them into 2 groups, so that means the vaccine didn't have anything to do, it was just random assignment to the 2 groups, then I would have expected a higher number of cases. But because I got such a low number of cases, that means that random assignment wasn't the reason that the number was so low, right? Because by random assignment, I could not have gotten such a low number.
Oh, okay. Yeah, I
Does that
get
make
it.
sense?
Yeah.
Okay, good. And now I am up to Sarah's question.
Okay, so it's a little bit like Rita's question, but I'm a bit confused because we started talking about if these 199 people would no matter what get polio, but are we kind of just ignoring that idea now since if if they were supposed to get polio, then having only 57 cases wouldn't work?
Right. So the idea is we are saying, okay, well, we're trying to prove something. Let's assume the opposite and prove that wrong, right? So we're saying, okay, what we're trying to show is that the vaccine works. But what we need to assume is that the vaccine does not work. Okay, we're going to assume that the vaccine does not work. And so if the vaccine doesn't work, that means that my low number of 57 was just caused by random chance. Okay, so I'm going to assume that the vaccine does not work, and therefore the number 57 was just caused by random chance. And what we've shown here is that that's really, really unlikely. Very unlikely. And because it's that unlikely, then our original assumption, the vaccine doesn't work, goes out the window. It's not an explanation anymore. Does that make sense?
I think so. Yeah.
Okay. All right. So that's our first experimental design that we can see. It's a complicated one. Well, not complicated. It's a complex one, but it's a very rich one in which we can see, okay, well, it's actually really, so you have some results and the results seem to tell, like, seem to tell a given story, but you can't get the full story until you have used some probability theory in order to confirm your results. And that's the advantage of statistics. It gives you the tool of probability theory to analyze and draw conclusions from the data that you have collected. Okay? So let's just define the parameters that we need for a given experiment, define what the different things that we're going to look at are, and then we will look at another little experiment that I did. Okay? So we have experiments. So whenever you're conducting a given experiment, you're going to have to make three main decisions. Those decisions are, what experimental material am I going to use? Which is just a complicated way to say that you're studying some units. So this is something that's called units. And it's particularly asking the question, on who am I going to conduct this experiment, or on what am I going to conduct this experiment, so that I can see exactly what it is that I am analyzing. The second thing that I can play with is what conditions am I going to study? Okay, and so this corresponds to something that we call the treatment. So that means, what am I going to subject my units to? So am I going to, I don't know, make them eat something, make them have to do something before I give a test. Maybe I'm going to give them a placebo or a vaccine, and so on, right? So the treatment is the different conditions that you're going to study on your units. And the third thing that we need to look at is what measurements we're going to make. And when we're measuring, when we're looking at the measurements to make, what we're trying to analyze is what is the outcome that we're going to study, right? So that means maybe I am evaluating the number of cases, in which case my outcome is going to be gets polio or doesn't get polio, but it could be a test result. It could be the time that it takes to complete a task. It could be the score that you get on a memory test. It can be anything at all, okay? So what measurements to make, and that's the outcome. The idea with experiments is that it allows us some control on some variability elements that are going to be included in any experiment that you run at all. So the problem with trying to prove that something is related to something else is that there's always several sources of variability. And those sources of variability are, first, variability, oh my God, variability that is planned and systematic. And so what this is going to correspond to is the treatments or the different conditions that you are studying, right? And it makes sense that this generates some variability because, for example, between the conditions placebo and vaccine, we want there to be a difference, right? We want there to be variation between these two groups. It's planned because you have introduced it into the system, right? Another type of variability that there is chance-like. So chance-like variability. Chance-like variability is what comes from random assignment. And the disadvantage of chance-like variability is that it is somewhat unpredictable, but the The disadvantage is that it's somewhat unpredictable, but the advantage is that it is measurable. So I can actually try to make some estimates of what I should expect in most cases, right? So it's measurable. Oops. So this can be measured. Measured. And so I can know what's normal and what's not normal. So that's what we just did, right? I created some simulation and I said, actually, what I observed was really unlikely. So I'm measuring how likely a given result is. So that's chance-like variability. And the third type of variability is called unplanned and systematic. And unplanned systematic variability is variability that we just don't know about, right? So maybe there are differences that we don't know about between some children and other children. That's what the researchers realized afterward when they were looking at the differences between the second graders and the first and third graders, right? They realized that the second graders that consented were on general higher income. So that was unplanned. They didn't know about it until after the study, but it was systematic. It was linked to the outcomes, but it didn't seem like it should have been linked, right? And so that means that it's unpredictable and we can't do much about it, right? So the whole point of experiments, so in experiments, what we want to do is minimize unplanned and systematic variability. Right? So the idea in minimizing unplanned and systematic variability is that then this allows us to differentiate the effects of our planned systematic variability. Right? So it allows us to differentiate, to identify the effects of our planned and systematic variability. And the star of experiments is really random assignment. The reason for that is that through random assignment, we are sure that we can we are trying to ensure that we can measure chance-like variability, and we are evening out the unplanned systematic variability. So I am trying to even out the level, the playing ground between the different groups that I'm comparing. Can I please see a show of hands for everybody that understands this? Okay, I'm excited to show you the next example. I want to know who in the class talked to their classmates about the guest percentages exercise. Everybody lower your hands. And I want a show of hands for who talked to your classmates about I mean, at this point, you've already completed it, so I just want to know if anybody talked about it with anyone. You followed my instructions. I am so moved. Okay, so that's good. Now, you were given a task. You had to estimate the percentage of UN countries that came from Africa. And all of you were given a random number, right? So you were given a random number between 0 and 100. What I would like to see now is who got the number 10. So I have about, I think I should have, yeah, I have 12 people more or less right now. Everybody lower your hands. That's fine if you don't remember. Okay, now who got the number 65? All right, so I have about, again, 10, 12 students that got the number 65. So how random do you think that number actually was? It was not random at all, right? I gave you two numbers. I mean, you were randomly assigned one of those two numbers, but it wasn't a random number between 0 and 100. So I might have lied to you. I apologize for that, but we're going to see the results of that little experiment. What I have looked at is the population of this class. What I have, so let me just try to think about that. Let's write this down. So then we have guessing percentages. So each student, so my units over here, let's just try to talk about that first. My units were you, okay, my arts and sciences students. So that was 2020 third semester arts and science students. Right? Then the treatment or the different conditions that I studied was whether you were primed. So I'll explain what I mean by this. Primed by the number 10 or 65. And the measurement, the outcome here, would be your guessed percentages. Now, I actually did not care about what percentage you guessed. I don't even know the answers to the question. Okay, maybe I should have looked that up right now, but I don't really care about that answer. What I'm really interested in is to see if your results confirmed something that is known in psychology known as anchoring. There's something called anchoring, the anchoring heuristic, which is something that humans tend to do, which is that if I suggest a value to you, you're going to, and then I ask you a question, what you're going to tend to do is to think about that value that I have just given you and probably pick a number that is close to that number. Right? So what you're going to do is you're going to remember the number that I just gave you, that means 10 or 65, and then you're going to unknowingly, without realizing, choose a number that is close to the value that I gave you. Okay, so that's what I'm trying to test here. So let me just explain what this is. This is that the estimate of an unknown quantity is influenced by a previously supplied starting point. Okay. So the question then is, do you think you fall within, so this only works if you don't know anything beforehand. Yes, that's right. So yeah, of course. So that's one of the things that I want to emphasize here. So one of the important things that we talked about last class, and that is also important here, is blindness. Right? So blindness is important because you needed not to know what I was testing, because otherwise you might have been like, oh, well, I'm gonna, I'm going to show her that she's wrong, and then you're going to pick a value that is not necessarily close to the one. So blindness is important because otherwise, so to avoid biases, right? So it would avoid you trying to, game the system and be like, no, I'm different than everyone else and I will not be fooled. And then the second thing is randomization here. Is also important because I don't know, maybe if I chose all of the students that did well in their high school geography classes, and then on one group, and then on the other group, I put everyone else, then I might bias my results. But even if I chose to say, okay, well, maybe everybody that had a birthday before this date will go into one group, and everyone that has a birthday after this date is going to go into another group, that might also introduce some biases. I don't know exactly which, but that's the whole point, right? I don't know what kind of biases I'm introducing if I don't use randomization. Okay, so that's the same thing here. So let's see. How did you do? The values of n are not right because I updated some results with some last minute answers that I got to the problem. Here we go. So this is the guessed percentage. So the values that you guessed. This is the anchor, which means the value that I gave you, and these are box plots, which you now know how to read. Okay, so what can you see from the box plots? Either on the chat or on the mic.
Number closer to 10 seemed to make more sense, so people tended to, align with it.
Mm-hmm.
Then, like with a number of 65, it seemed a bit too high to make like rational sense for
Right, and yet.
a world country, so people tended to not, associate completely with it, but they still tended to guess higher. And
Mm-hmm. So a couple of things there, right? So the first thing is that everybody seems to have some kind of use of reason, which means you're not going to guess that all of the UN countries come from Africa, which makes sense, right? But what you can see is that the people that were primed with the number 10 are going to choose values that are in general closer to the value of 10, which is about here. And even though, of course, the people that were proposed the number 65 are not going to be giving a value close to 65, they're still going to give values that are pretty high and definitely significantly higher than the values for those of you who had a value of 10. Right? The range for 65 is indeed much bigger than the range for 10. And the reason for that is, again, that some of the students really wanted to be like, okay, like try to reason it out on the one hand, but the typical response here is to choose higher values, right? All right, Sarah's saying the real answer is around 25, it seems like. So nobody did too well. There was so 25 is maybe around here, which means that there were still a lot of people that chose lower values for 10, and definitely for 65, you were not that many. Can I see a show of hands for everybody that understands this? And does everyone here understand how this corresponds to an experiment? Yeah. Okay, so this is just one small example of a type of experiment that you could try, for example, in your research report. But, oh, the answer is 28. Thanks, Eloise. There you go. So even further away from here. Okay, so now just a couple of things before I let you go. Again, it's not taking too long. So homework 2 is now posted, now available. It has some problems about linear transformations and some problems about experiments. In addition to this, in the YouTube prep channel, there's a little video that is called "A Lady Tasting Tea," which is an experiment that I would like you to just watch the video. It's 2 minutes, so you can just look at that and try to think about, what the units, what the treatment, and what the outcome is. And lastly, if you want to get inspired about types of experiments that you could try out, and you have access to Netflix, this is one of them. So if you have access to Netflix, there is a show that's called 100 Humans, in which they conduct quite a few experiments. Not all of them are very experimentally sound or very, like um, well designed, but it is a good way of trying to understand how you can do experimental design. It might be some inspiration for your project. So that might be a good you know way to think about it. And aside from that, there you go. So you watched it. That's good. Um, so draw inspiration from that. Have a nice weekend, and I'll see you on Wednesday. If you have any questions, you can always let me know. Bye bye. There's no web work. Not this week. So you have the homework, but no web work.